Welcome to everybody. So we're really very pleased to have this new edition of the CRM Colloquium, in which Professor Tao, which is, as you know, a Fields Medal and also a full professor at the University at UCLA, will give us a lecture on machine-assisted proofs. I think that it's really amazing to have such an amount of people assisting to a colloquium. Colloquium is the first time that I think we have almost 300 people that have registered to be here, and we're really, really very happy. This is a very top level that we have to maintain in the future. So I am going to be very briefly, and I'm going to introduce you also to, well, everybody knows Eva Miranda, but she is also an ICREA Academia and full professor at the UPC, University Polytechnic de Catalunya, and she's going to give us an introduction to the work of Terence Tao. So, thank you very much.
Okay, it's an absolute honor to introduce Professor Terence Tao from the University of California, Los Angeles. Professor Tao has received numerous distinctions throughout his career, and from what I learned from the organizers, far too many to list them all today. We have to finish in time. But I'll highlight a few. Among them are the Fields Medal. Remember that this was awarded in 2006 in Madrid, so not very far from here. And the Breakthrough Prize in Mathematics in 2014. One of his earlier accolades was the Salem Prize in 2000. He received the Royal Medal from the Royal Society in 2014, and more recently, La Grande Médaille from the French Academy of Sciences in 2022. He was the first recipient, the first of many things, but in particular the first recipient of the Riemann Prize in 2019. And in 2020, he was honored with the Princess of Asturias Award for Technical and Scientific Research, also not so far from here, and one of the highest awards conferred in Spain in science. Professor Tao's mathematical journey began very early. He started his participation in the International Mathematical Olympiads at the age of 10, earned his PhD from Princeton University at the age of 21, and became full professor at UCLA at the age of 24. His extraordinary talent earned him the title of Mozart of mathematics in the media. His research covers a wide range of areas, including harmonic analysis, partial differential equations, geometric and arithmetic combinatorics, analytic number theory, compressed sensing, probability theory, algebraic combinatories, and to name a few. So after seeing the range of his work, I'm tempted to add a new denomination to the list and call him the Leonardo da Vinci of mathematics. What makes him stand out even more is how he shares his love and passion for mathematics with the world. His blog, What's New, takes the genius of mathematics and much like a chef in the world of the constructed cuisine, breaks it down for us, showing the creative process behind problem solving and the excitement it brings. In addition to his mathematical achievements, Professor Tao has shown his important commitment to society. As one of the members of the President Council of Advisors of Science and Technology in the United States, he has taken a step beyond academia, offering his expertise to guide policy decisions. We will learn more from mathematics and society later today. He has also redefined the way mathematical collaboration happens. His involvement in the forefront of the Polymath project, particularly Polymath 1 and Polymath 5, has shown that solving problems in mathematics can be a massively collaborative effort, evolving the traditional image of the mathematician working alone. Today, Professor Tao will continue to push the boundaries of how we think about mathematics, and he will talk about machine-assisted proofs. So please join me in welcoming Professor Tao.
Thank you very much, Eva. This has been a great week so far, and a lot of events. So the title of my talk is Machine-Assisted Proof. I should actually change the title. I put AI in mathematics to make it sound more sexy, I guess. But AI is only a small portion of what I'll be talking about. Actually, and this talk will actually overlap a lot. Those of you who were at the talks just previously, actually, I even used the same examples in some of the previous talks. So you'll see some, those of you who were there an hour ago will see some repetition. Yeah, so I'll be talking about how machines have been used to assist mathematicians in the past, present, and future. So how long have mathematicians been using machines to help them prove things or compute things? Well, really for thousands of years. Here is a very early machine that was used by mathematicians in Abacus to compute things. So we've been using machines for for thousands of years. What about computers? So even computers we've been using for centuries. Here is an early computing cluster from World War II. So during World War II, they needed lots and lots of computations for ballistics, also the Manhattan Project. And all the men were busy doing something. So it turned out that a lot of women were hired with adding machines, so mechanical computers, mechanical human computers. In fact, at the time, the standard unit of computing was not the flop or the CPU, it was the kilojoule hour. How much computing you could do with 1,000 girls in a room for 1 hour. So one of the most early uses of computers was to build tables. So maybe the most famous early tables are the logarithmic tables of Napier, and then there were tables of other trigonometric functions and other special functions. And those were built by human computers and were extremely important in early modern mathematics. We still use tables today. I mean, we don't use these tables today, but we just call them something else. We call them databases. But databases are still basically tables. And they're essential in what you might call experimental mathematics. And so it's actually a lot of the focus of the previous talk was discovering, using data from these tables to conjecture new mathematics. So I have some examples which are almost exactly the same examples actually from the previous talk. I didn't realize that. But so one famous early example was Legendre and Gauss constructed tables of the first 100,000 prime numbers or so. And Gauss used this, and so did Legendre actually, although his conjecture was off by a small amount, but to conjecture what we now call the prime number theorem, the most basic theorem in analytic number theory. And then a century or two later, Birch, Swinton, and Dyer very similarly used tables of elliptic curves, now generated by early computers, to formulate a very influential conjecture still open also in number theory, called the Birch, Swinton, and Dyer conjecture. Perhaps the biggest database of all, the biggest table of all in mathematics currently is the online encyclopedia of integer sequences. So this is a huge database of hundreds and thousands of integer sequences. So things like the Fibonacci numbers, 1, 1, 2, 3, 5, 8, that's in the database. And so are hundreds of thousands of other examples. And actually, many mathematical theorems have been proven basically by studying an object, trying to find out what else is known about this object, and then associating some sequence of numbers to it. Maybe you have a sequence of manifolds, you compute the dimension, or some rank or something, and you look it up in the OEIS, and there's a good chance that somebody somewhere has studied the same sequence. And maybe because it came from a different area of mathematics, you've discovered a new connection between these two areas of mathematics. And many interesting results have come this way. I've used the OEIS to well, okay, I often use it when there's some combinatorial problem I want to solve, but often it's, rather than working out by pen and paper, it's much faster to just work out the first 5 values of whatever I'm computing and then consult the OEA is usually there. And nowadays, databases are also being input into machine learning algorithms, and we saw that actually the previous talk was about this, to discover new phenomena such as murmurations of elliptic curves. So that's one very classical way in which computers and machines have been used. The other very classical way to use computers is through computation, scientific computation, number crunching. Just using computers to calculate very complex calculations. Perhaps the earliest example of a scientific computation, or one of the earliest, was in the 1920s when Lorentz was tasked in the Netherlands. They were building a giant new dam, which is one thing the Netherlands are really good at, and they wanted to model what was the effect on how the water currents would change when the dam was installed. And so Lorentz assembled a cluster of human computers, because that's what he had at the time, to compute the effects of fluid flow using some very basic modeling. It's notable, actually, this is one of the first places, he had to invent floating point arithmetic in order to do this calculation, which of course we still use today in our modern computers. So of course we use scientific computation all the time now. We simulate all kinds of things, nuclear reactions, the weather. It's not just simulating equations and PDEs and so forth. We can also do lots and lots of algebra. We can find bases for ideals. We can solve huge systems of nonlinear equations using lots and lots of standard software packages, Magma, Mathematica, Sage, and so forth. And these are very common tools now. They're basically just advanced calculators for us. There's various levels of precision you can use. So floating point arithmetic is very fast, for instance, but it does have some errors. It has round-off errors. It's not completely precise. But there are more precise versions of arithmetic, like interval arithmetic, that you can use. So one thing that's sometimes done is that sometimes you do an initial rough calculation using floating point arithmetic, which is fast, and then you correct it and you check it using interval arithmetic once you get an approximate solution. Another type of scientific computation are SAT solvers, or SAT solvers, or satisfiability modular theory solvers, SMT solvers. So these are quite sophisticated pieces of software where you can input all kinds of hypotheses, like maybe there's 1,000 variables which are true or false, and you input various hypotheses, like maybe the 3rd variable and the 5th variable and the 7th variable, at least one of the statements is true, or maybe one of them is false, and you input many statements like that. These are called satisfiability clauses, and then maybe you also have some theory, maybe you have some operations like addition and multiplication, and you have some theories like maybe some laws like the commutative law, the associative law, and you ask what can you deduce using these hypotheses. Now this is an NP-hard problem in general, so the complexity of solving these problems rises at least exponentially, at least as far as we know, with the number of variables, but still for medium-sized problems, say 1,000 variables and so forth, SMT solvers are able to do these massive computations and prove theorems that no human could ever hope to solve on their own. Here's a typical example. There was a conjecture in what's called Ramsey theory, called the Pythagorean triples conjecture, that if you take the natural numbers and you color them into several colors, let's say 5 different colors, the conjecture is that one of these colors must contain, one of the color classes, must contain a Pythagorean triple, 3 numbers A, B, and C that form the angles of the sides of a right angle triangle, like 3, 4, 5. So that's not known. It's been a challenge for Ramsey theorists to try to prove. You can prove simpler patterns, like x plus y equals z, but not x squared plus y squared equals z squared. However, for 2 colors, it is now known. We now know that if you color the integers into 2 colors, if you only color the integers up to 7,824, we know that there is a way to do it in which neither color class contains a Pythagorean triple. That's not too hard. You just write down, you just find a coloring, and a very easy computer program can check there's no Pythagorean triples. The hard part is showing that if instead you color 7,825, the numbers up to 7825 into two colors, there are 2 to the 7825 ways to do that, but no matter which way you do it, one of the colors will contain a Pythagorean triple. And that's not easy, so that was a massive sat solver calculation done in 2016. At the time, it claimed the record for the world's longest proof. So the proof actually generated a proof certificate that actually verified the calculation. It was 200 terabytes long. So that's an extremely long proof. It was since compressed to a much smaller, much more manageable 86 gigabytes. But still, and there's since been, I think it's now only the second largest proof in existence. But it was an amazing calculation. Okay, so these are sort of the classical ways in which we've been using computers to build databases and to do scientific computation. But in recent years, there have been emerging ways to use computers, and of course we also use computers for mundane things like doing an email and writing papers. I'm not going to talk about that sense in which we use computers. But there are sort of three new directions in which computers are being useful to do mathematics. Individually, they're beginning to have some niche uses, but what's really exciting is that they're beginning to get combined with each other, and also combined with the existing databases and scientific computation tools. And together, all these tools are beginning to do things that really we wouldn't have been able to do previously. So the three tools I'm talking about are, first of all, machine learning algorithms using things like neural networks to predict answers based on data to various mathematical problems. And it's beginning to be used to generate conjectures or to guess solutions to various complicated problems. Then there's these famous large language models like ChatGPT and Claude and so forth, which you can interact with at a natural language level. And they are beginning to at least sound like research-level mathematicians if you talk to them. They still struggle actually delivering the content of a research-level mathematician, but they at least have the form of it. And they're beginning to be able to suggest some strategies and be able to generate at least very small proofs. And then there are these proof assistants, which are not AI in the sense of the previous two, in that they're not sort of using data to make predictions, but these are computer languages that can verify proofs, that can give you a 100% guarantee that a certain proof is correct. You have to write the proof in a specialized language, but it gives you a 100% proof guarantee that the proof, that your statement has actually been proved, as long as you've translated the proof correctly, the statement correctly into this language. So by themselves, they're quite tedious to use, but they look like they will combine very well, particularly with the large language models, and they will fix the biggest problem that these models have, which is that the models make lots and lots of mistakes. Well, they don't completely fix it, but they at least get rid of the false positives. Okay, so I think in my slides I'll talk about the proof assistants first. So proof assistants are ways to check proofs that are very complicated, and they're particularly useful for proofs that already have a computer component with them. So the first maybe really computer-assisted proof in the literature was the proof of four-color theorem in 1976. That wasn't a formal proof by modern standards. This proof required, there was a table of like 1,000 graphs or so, and there were various properties these graphs, Apple and Haken claimed these graphs had various properties. Some of these properties could be checked by the computers at the time, but there was another property that had to be checked by hand. In fact, I think that the daughter of Haken had to by hand verify some very difficult combinatorial claims for each one of these 1,000 different graphs. And so that the proof is actually a weird mix of computer code or punch cards, actually, I think, and microfilm of this poor daughter, Dorothea, doing all these by hand calculations. And it had lots of errors, unfortunately. It was only 2 decades later that an actually computer verifiable proof was written, that Robertson et al. Found a slightly different proof of the same theorem, where the claims to be verified could actually be verified with 2 pages of 200 lines of computer code, and you just had to trust that the computer code was actually programming what didn't have any bugs in it, but it was a code that anyone could run, or they could write their own code. And then finally, there was the 100% guarantee of the four-color theorem, where there was a completely, the proof was completely written in a language specifically designed to give proof certificates. In this case, the language Coq was given only in 2005. So it took 30 years or so before we had a completely verified proof of this theorem. Now, since then, we've become better at formalizing proofs. So the next major result to be formalized was the proof of the Kepler conjecture. So the Kepler conjecture is an old conjecture about the most efficient way to pack unit balls, unit spheres in 3 dimensions. You'll see a talk later this week actually about packing spheres in higher dimensions. But in 3 dimensions, there's this classic conjecture of Kepler. There's sort of an obvious way to stack cubes with each other, which is the same way you see oranges packed in a supermarket. It's called the hexagonal close packing. There's also a dual packing called the cubic close packing, and they both have the same density. If you look at how much space is occupied by the spheres, it turns out to be about 70%. It's number pi over 3 root 2. And this was conjectured to be the optimal density for any packing of spheres. So this turned out to be really hard. I mean, it is an optimization problem, but it's an optimization problem in infinitely many variables. There are infinitely many cubes, each one is spheres, and each one is located, there's 3, you have to write down 3 numbers for each location of each cube, each sphere. So there's, you can't get a computer to directly solve this problem. As far back as 1950, it was observed there was a strategy that could solve the problem in principle with some sort of finite computation. So the idea is you don't look at the spheres, but you look at certain polyhedra around each sphere. So around each sphere, there's something called the Voronoi cell. That's all the points that are closer to the center of the sphere than to the center of any other sphere. And so every time you have a sphere packing, it decomposes space into these Voronoi cells, these polytopes that are adjacent to each other. And each cell has a certain volume, and they have some number of faces, and they have some neighbors, and the neighbors have volumes. And what Toth observed is that if you could prove some linear inequalities about how the volume of a polytope of a Voronoi cell was related to the volume of nearby Voronoi cells, you could take linear combinations of these inequalities, and then you average over all the cells, and if you do it correctly, you can get some upper bound on the density of the packing. And if you do it really, really well, you could maybe get the exact bound, pi over 3 root 2 of the packing. So so all you need to do is somehow collect enough linear inequalities between volumes of Voronoi cells and plug it into some linear programming algorithm, and you might be able to get to solve this problem. So many people tried to do this, and there were even, this is one of these problems which is famous for tracking a lot of incorrect proofs. But this, nothing worked. I think you could get some bounds, but not close to this pi over 3 root 2. But in the 90s, Thomas Hales, and then I think also Ferguson is, later on, was working on a way to modify this scheme where you don't work with the Voronoi cells, but you work with a more complicated decomposition than the standard Voronoi decomposition. And you don't just work with volumes, you work with what he called a score function, which is sort of a volume with several additional adjustment terms added to it. But still, the basic strategy was the same, was that you have these polyhedra with scores, and you have to develop these linear inequalities, and you try to optimize them and get a good bound. And so he worked for almost a decade on this. So here's a quote. So he worked with Samuel Ferguson. He says, Ferguson and I realized that every time we encountered difficulties with solving this minimization problem, you could just adjust the scoring function to skirt the difficulty. The scoring function became more complicated, but with each change, we could shave months or years from our previous work. But this incessant fiddling was unpopular with my colleagues. Every time I present my work in progress at a conference, I was minimizing a different function. Even worse, the function was mildly incompatible with what I did in earlier papers, and this required going back and patching the earlier papers. So in '98, Hales and Ferguson did announce that they had finally solved the problem. They had found a score function, and they could solve an optimization problem in 150 variables, and they could actually get exactly this pi over 3 root 2 optimization. Now, initially they were hoping to do it just by pen and paper, but it was so complicated they had no choice to use a computer. So the proof was, by the standards of 1988, the proof was massive. It was 250 pages of notes and 3 gigabytes of programs and data. Now, it was not universally accepted by the community at the time. It was accepted at Annals, but it took 4 years and a panel of 12 referees to, and even then the referees they said they're only 99% certain of the correctness of the proof because they could not certify the correctness of the computer calculations. So Annals did publish the paper, but they actually added a little a disclaimer at the beginning. So we do not guarantee the correctness of the calculation. They have since removed this this disclaimer. But anyway, the point is that this was a result where there was really serious doubt as to whether the result was completely correct. And so there was, at least for Hales, a huge incentive to actually formalize the proof in a way that removed all doubt. So he introduced this project he called FlySpec, I'm not quite sure why, to translate the conjecture, the proof that he had, into the proof of language of a proof assistant to formally verify. He estimated this would take 20 years to do. It was a very complicated proof, and with the technology of the time, every time you want to formalize anything, you have to sort of decompose it all the way back to the axioms of mathematics. So it's like even very simple things like I don't know, the area of a triangle is half base times height. This requires a proof. And like every single thing needed a proof. So yeah, he estimated 20 years, but it only took 12 years. With 21 collaborators, but he was able to eventually, in 2014, using the proof assistants Isabel and HOL, finally able to formally settle this conjecture. And now it's pretty much accepted by the community that this conjecture has been proven. A more recent experiment is what's called the liquid tensor experiment of Peter Schulze. It's named after a rock band, actually. So this concerns Schulze's theory of condensed mathematics, which is an attempt, is a theory he has proposed to sort of introduce the power of category theory, which is very useful in algebra and topology, into analysis to study things like topological groups or Banach spaces and so forth. So unfortunately, if you look, Banach spaces and topological groups and so forth, they are categories, but they're not very good categories. They're not, for example, they're not abelian categories, if you know what they are. So from a category theory point of view, they're difficult to work with, and this is reflected in, there's many reasons for this, but analysts really don't use category theory very much. The most powerful tools of category theory are not really useful for the standard categories that we use in analysis. But Schulze proposed replacing these categories with slight modifications of categories, a little bit like replacing varieties with schemes, if you know some algebraic geometry, which have better category theoretic properties, but still are very related to the classical topological categories that we care about in analysis. So there's a category of condensed abelian groups. There's the category of what's called liquid vector spaces. But in order for it to work, there's a certain vanishing theorem which I will not attempt because I don't even understand it myself. So there's a category of liquid Banach spaces or P Banach spaces, and attached to it there's a certain X group over the category of condensed abelian groups, and a certain category theoretic sort of homology type group has to vanish. And this makes most of the rest of the theory actually useful. So there's this difficult result of Clausen and Schulze, which underlies the whole theory. It's like the fundamental theorem of the subject. So Schulze wrote in a blog post, he spent a full year obsessed with the proof of this theorem, almost getting crazy over it. In the end, we were able to get an argument pinned down on paper, but no one else has dared look at the details of this, and there still some small lingering doubts. With this theorem, the hope that the condensed formalism can be fruitfully applied to real function analysis stands or falls. This theorem is of the utmost foundational importance, so being 99.9% sure is not enough. I was very happy to see many study groups on condensed mathematics throughout the world, but all of them have stopped short of this proof. This proof is not much fun. So he says that this is my most important theorem to date, which is quite a strong statement, actually. Better be sure that it's correct. So he proposed an experiment to see if he can formalize it in now a very modern language Lean, which was only developed a few years ago. So it's similar to the previous proof-assistant languages. One feature of it which gives it somewhat of an advantage, I think, is that it has a very well-developed library. So as I said, in previous languages, pretty much every basic statement that you want to use in, say, undergraduate level mathematics, you have to prove from scratch. Lean has this mathlib project where it's been trying to collect all these basic statements in mathematics and provide proofs of them. And it's just a huge library that you can just import into, just like you import a library in, say, Python, into any future Lean project. And so you can start from a base of roughly undergraduate level mathematics rather than from like the axioms or set theory. So that gives you a bit more of a head start. The dream is to get to the point where like most of graduate school level mathematics is in this library. That would give it be even better. And so this took only 18 months to do. It was actually quite instrumental with a lot of help from people in the Lean community, in particular Johan Kummerlin and Adam Topaz. And actually, there was a lot of synergy. So the way these formalization projects work is that you don't just take the proof and you start typing in Lean. That turns out, I mean, for very small proofs you can do that, but for anything complicated, you need a plan. The first step in any modern formalization project is to write what we call a blueprint, which is a version of the proof which is still readable by humans, or at least humans who understand condensed mathematics, but broken up into lots and lots of little steps. So your big theorem is now turned into 100 little lemmas. Each lemma has maybe a 5-line proof. And so it's like a very, very pedantic version of the proof that you'd see in a paper. But then once you split it up, then people can work on formalizing each little piece separately. And you don't necessarily need to know the status of all the other lemmas. Every proof you can have is just conditional, that if the previous lemmas are proven, then you can guarantee the conclusion of your current theorem. And so this blueprint was written in the first few weeks. I think Schulze said that it made him understand the proof much better, actually just after writing this blueprint. And then over time, slowly, each of the little sublemmas was proven. There's actually, and once you have the proof, you can actually go the other way. So there's now, I'll show you in a few slides what a formal proof looks like. It's not as human readable as the blueprint, but you can actually take a proof, well, some proofs at least, that are written in Lean, you can actually convert back into something that looks like a blueprint. So here, for example, there's a certain topological statement. It points at topology. There's a criterion for a function to be continuous. And it was proven in Lean, and this is an automatic translation of a Lean proof back into a human readable proof. So now it looks like something that you might see in, say, a topology textbook. So it looks like a human readable proof, but it's more interactive. So like you can click, this particular PDF is not interactive, but you can click on any location in this proof, and it will tell you what the current hypotheses are, what all your assumptions are, and what you're trying to prove at any given step. If there's a step which is just claimed, you can click on it, and it will tell you the justification of that step, and you can expand and contract different components of the proof as well. I think in the future, textbooks will be written in this format. I think it can be much more interactive than they are today. So I myself ran a formalization project last year. Last year I proved a conjecture in combinatorics. It's not super important what the conjecture is. It's classifying sets of small doubling in elementary 2 groups. But never mind exactly what the statement is. So we proved it in the traditional way. We emailed each other. We had a strategy. We proved it. We wrote a paper, a traditional paper, 33 pages. Being combinatorial, it didn't need that much previous theory. So one thing about the liquid tensor project is that Schulze had to, the formalization project had to develop lots of results about, say, sheaf theory, category theory, lots of things that weren't actually in mathlib. But now they are, actually, because of this project. Mathlib is much more enriched it knows what a topos is and so forth. This we thought would be simpler because combinatorics has fewer prerequisites. But it was still somewhat tricky to formalize. But we did it in record time. So now it takes it took 3 weeks to formalize this. So the time to formalize has been going down quite a bit. I would say at this stage, the time to formalize a proof is roughly maybe 5 to 10 times the time it would take to write a proof. And that's assuming some optimal conditions, which is not great. It means that we're still far from having a vast fraction of the mathematical literature formalized. But with AI tools, I think the fraction should go down quite a bit. And actually with AI, there's no reason why it won't go down below 1. I think once the AI assistant becomes effective enough, it will actually be faster to write a paper by explaining your proof to an AI who will formalize it and write down the LaTeX instead of typing the LaTeX directly. But we are not at that stage yet. So how did we do our formalization? So we broke up, again, with the first step is to write a blueprint. We broke up our main theorem into like 100 or so different lemmas. And one nice thing about the blueprint software we use is that it creates this little dependency graph. So the final statement is called the PFR conjecture. The final statement was there's a little bubble, and this bubble was white. At this stage, the bubble was white, which means that it hasn't been proven yet. In fact, actually, this was at such an early stage that even the statement of this theorem had not actually been formalized, let alone the proof. That's why it's white. A blue bubble is a statement which has been formalized. The statement has been formalized, but the proof has not been formalized. And a green bubble is one where the proof and the statement and the proof have been formalized. And the arrows indicate logical dependency. So in order to prove this theorem, it relies on these previous statements. So at any given point in time, you can just open up the blueprint, and it will show you this graph, and you can see what has been proven, what needs to be done. It's a very nice way to organize the project. And then different people can just pick a bubble and say, oh yeah, I'm going to work on this bubble, and so forth. So for example, this is a simple statement. So there's this quantity called Rouget distance. I'm not going to define it here. And one of the basic lemmas of this distance is that, like any metric distance, it is non-negative. So this was a basic tool that we needed. It's very simple to prove. It just needs one other previous lemma. So this is an example of one tiny little atomic piece of the project. And so this is what the proof looks like. Okay, so so this is what lean looks like. We're trying to prove that something is non-negative. This is what the statement looks like in lean. So it looks kind of like the actual statement, just with a slightly different syntax. And it's proven using a bunch of tools. Okay, so this routine, this is an inequality between relating this distance to something called entropy. And that is the previous bubble. That corresponds to this previous bubble here. GE trans is the transitivity of the less than sign. Like if A is bigger than B and B is bigger than C, then A is bigger than C. That's this statement here. So this is not completely human readable, but if you know some lean, you can pass this without too much difficulty. So the nice thing about this is that you don't need to understand the whole proof. So we had 20 people. Most of them didn't come from combinatorics. So in fact, a lot of what was needed was that we used the theory of Shannon entropy in our proof. And at the time, this theory was not in Lean's math library. So we needed some probability theorists to come in and develop the theory of Shannon entropy. And so they did that, and they could do that more or less in parallel with the rest of the project. And so you can really collaborate with lots of people who you wouldn't normally collaborate with because you don't need to communicate the entire project to these other people. And also, you don't even need to trust the other people. So, collaborations in mathematics, they rarely get above like 2 or 3 or like 5 people. You rarely see collaborations with more than 5 people. Because in mathematics, you have to trust every single contribution of your co-authors. If there's one error that one co-author introduces, your whole argument can collapse. But the way it's structured, is organized using GitHub. You upload your proposed your new proofs, and the Lean compiler automatically checks whether the contributions are correct or not. So you don't need to trust the contributions. So we have contributions from complete strangers, even non-mathematicians. There are people who are basically, they're math adjacent, maybe they were trained as undergraduates in mathematicians, and they became programmers, or they like solving puzzles. And so there's actually many people who maybe are not professional mathematicians, but they're very good at finding 5-line proofs for very, very, like these sorts. They're almost like solving like little Sudoku puzzles or something. So it's allowing for many much broader collaborations than were previously possible. Yeah, well, okay, so it worked. I mean, we weren't really in doubt. So unlike the previous examples, we weren't really in doubt that this theorem wasn't proven. But it was a good test case. We added to Lean's math library because of it. It still takes longer to formalize the proof than to write it. But curiously, if you want to modify the proof, it's actually faster to do it formally. So there was a constant. Okay, so there was a constant 12 that showed up in this theorem. Later on, we improved the 12 to an 11. We found some way to run the argument faster. Now, normally, if you want to make a change like that and you have a 33-page proof, you basically have to rewrite the entire paper, changing constants all over the place. And if you make one little error in your computation, you have to start over. But actually, it took like a day or two to implement this refinement. You basically just change 12 to 11 in the main statement, and then the compiler runs, and it flags like 10 places where things don't compile anymore. And then you go to those 10 places, you change those, and then there's 10 more places. But like it instantly figures out what needs to be changed. Whereas if you do it by pen and paper, you have to check line by line by humans, and you make lots of mistakes. So it's already faster than a human for certain specialized proofwriting tasks. This was a relatively small project. There are now much more ambitious formalization projects. The biggest one right now is Kevin Buzzard's 5-year project to formalize the proof of Fermat's last theorem. So he has a blueprint, and he's just started. Bits and pieces of it are beginning to be formalized. It's unlikely that, well, so here the problem is that there's a lot of prerequisites which are themselves giant papers. And if you want to formalize every single step, this will probably take more than 5 years. His more modest goal is to conditionally prove Fermat's last theorem, assuming results that were in the literature prior to the proof of Fermat's last theorem. So that I think is a reasonable goal for these 5. Okay, so that is proof assistance. Machine learning, there's actually been 3 talks already, at least, on this topic this week. So machine learning creates ways to generate new solutions or propose solutions to various problems. There is, for example, it's being used to propose ways in which the fluid equations, such as the Euler equations, can exhibit singularities, quantum blow-up, and we already had many talks on this already, so I'll be very brief here. One thing is that these tools, they don't give absolute guarantees, they don't produce exact solutions. They generate approximate solutions, and there's some score that you can try to maximize to see how good a solution they can be. They don't actually generate rigorously accurate solutions, but it turns out that in some cases, once you have a good enough solution, approximate solution, you can use rigorous perturbation theory to convert your approximate solution to an exact solution. And this often requires more traditional scientific computation tools. But there are ways to combine these not quite reliable but very powerful machine learning tools with more reliable scientific computation tools to do things like create new blow-up solutions to the Euler equations. So this is a program that's still in progress. We haven't yet actually created a blow-up to the full 3-dimensional Euler equations with the strategy, but we've done it for other simpler models so far. The big prize actually is to make the strategy work for Navier-Stokes. And we had actually a talk about that yesterday. That is still a bit out of reach. I mean, in principle, it could work, but many steps are not complete. But I won't talk about that since it's been covered in many other talks this week. I'll talk about another really nice application of machine learning, which was also mentioned actually in the previous talk, which is the use of machine learning to prove a new theorem in knot theory by Davies, Juhas, Lackenby, and Tomasev. So the thing about machine learning is that it only works when you have a lot of data to train on. And in many fields of mathematics, we don't have enough data. So there's a few in which we do have data. So the OAIS gives you lots of data on sequences, there's lots of data on L functions and the curves, and there's lots of data on knots. So people actually have taken the time to create millions and millions of knots and identify various features of these knots. So knot theorists study these called knot invariants. And so to any knot, there are various important numbers, invariants that you can assign to these knots, and these are topological invariants of the knot. There's something called the signature, which is a combinatorial invariant. It involves something called the linking form. There are these geometric invariants called hyperbolic invariants. If you take the complement of a knot, that turns out to be a hyperbolic space, and you can keep it as volume, and there's some surface areas and some various geometric objects, statistics, like real and complex numbers, that you can assign to most knots. There's some knots that are called torus knots, which are not hyperbolic, but most knots come with statistics. And people have constructed massive databases of knots and all these statistics. And so and you can start inserting these into, feeding these into a neural network, and trying to see if there are any previously undiscovered connections between these statistics. So, for example, one thing you can try to test it on is that suppose you only give the neural network the hyperbolic invariants, which come from geometry. Can you use the hyperbolic invariants, which are this list of 20 numbers, to predict the signature, which is a certain integer, which is a combinatorial invariant? A priori, these are completely different fields of mathematics. There is no obvious link between the combinatorial invariant and the geometric invariants. In fact, I think the people who study knot theory, combinatorial knot theory, are almost a disjoint set of people even. It's even a different field than the geometric knot theorists. But still, using a neural network and a database of about 2 million knots, about half of which were generated purely for this problem, these authors found that you could actually predict, just from the hyperbolic invariants, you could predict the signature with like a 90% accuracy. And so this was a huge, huge clue that there was a connection between these two statistics, but it didn't really tell you what the connection was. Well, technically it did. It gave you this really complicated function, this neural net, which is just a massively nonlinear function, which if you can give it any 20 inputs of numbers, and it would spit out a prediction. But it's kind of like this black box. You can't just look at it and obviously see what it's doing. But it's a function, and you can analyze the function. So by various things, by various techniques. So what they did was something relatively simple. There are more advanced things you can do, but it turns out that a relatively simple technique worked in this case. They did what's called a saliency analysis. So you have 20 different inputs, 20 numbers that come in, and one number that comes out. So you can take one of these numbers and you can just vary it, jiggle it up and down, and you can see how much varying one input affects the output. And that's called the saliency of that input. And it turns out that of the 20 inputs, only 3 of them had high saliency. So only 3 of them, only 3 of the statistics, as the longitudinal translation and the real and imaginary parts of the Meridiano translation, which is a complex number. These are the only 3 inputs that had a significant impact on the signature, which was a big surprise. For example, the volume, which was previously thought to be the most important invariant in this problem, actually had almost no impact at all. So that was a surprise. But once you have this clue, then you can do further analysis. So now there's only 3 inputs that you care about and that are important, and one output. So what you can do is you can just start plotting, scatter plotting your 3 inputs against one output. That's a 4-dimensional plot, and you can take various slices of it, and you can basically visualize it with the human eye, with color charts and so forth. And so they started plotting the database of a million knots with the variables they isolated, and they could visually see patterns. And so at this point, they then used the human neural nets, to guess what the patterns were, and they started making conjectures. And so they're able to conjecture an inequality between the signature and the translations. It turned out that once they had the conjecture, they could then use the database and the neural nets actually found a counterexample to their conjecture. But then they looked at the counterexample. They saw how they understood why the counterexample was breaking their conjecture, and they corrected the conjecture to add one more term to it. And that was a conjecture that passed, that sort of passed all the neural net tests. And once they had the right conjecture, they could see how to prove it. And so then they actually had a theorem, and so they published a paper explaining everything. So it's a very nice interplay between human mathematics and machine mathematics. They did something that neither the human alone or the machine alone could do, but it was really the interplay between them that got results. And I think that's a very promising paradigm for the future. Okay, so the splashiest development in recent years is, of course, these large language models like ChatGPT and Claude and so forth. And so these are models where you can take arbitrary text prompts, and in fact nowadays they're even multimodal. You can upload PDFs or speech and so forth, and it will give back a response. Again, just using a very fancy version of a neural net called a transformer, and it's just sort of guessing what the response is word by word. It just completes the answer given the prompt. And so you can feed it a math question, and it can try. It can try to guess the answer. It's like bringing a student up to the board and just asking the student code to write down from scratch what the answer is. It usually doesn't work, but occasionally it does. So, for example, I mean, the technology is improving at a rapid rate, but even from last year, GPT-4, they tested it on many, many different problems in the IMO. And I think for 99% of the problems, it did not come close to solving the problem. But there was like 1% of problems for which it actually managed to get a correct solution, which at the time was a very impressive achievement. We can since do better, but yeah. So this is one problem. A problem in functional analysis. You have a functional inequality, and you want to solve the equation. And it turns out that this is a problem where you really can just go up to the board and just try the first thing that comes to your mind. And occasionally, this particular problem, it actually works. So it actually gives a complete proof. It's cheating a little bit. This form of the question is not quite the form of in the IMO. The researcher actually modified the problem to make it slight. For example, I think the question was prove or disprove if something was true, and they said instead to actually prove it. Which is actually a big clue, but still. But so it can be very impressive. It can also be very unimpressive. So these models are not actually computing based on actually understanding what they're doing. They're statistically matching. Like they're just figuring out what is the most logical thing to say next. So for example, back last year, they gave it a very simple arithmetic problem. What is 7 times 4 plus 8 times 8? And the models just said, what is the most likely next token? And for some reason, it came out 120. It's based on previous training data on previous arithmetic problems. But then it paused, and it decided that it needed some explanation. So it's, okay, to explain it, I'm going to do it step by step. And so I do the step-by-step calculation. And it came out with actually the correct answer of 92, which is different from the answer that I first guessed. And then the researcher pointed out, but wait, you said the answer was 120. And then he just said, oh, sorry, that was a typo. The correct answer is 92. So it doesn't have the ground truth. Now, there are ways to sort of artificially fix this. Like you can force the model to call a calculator or call some more fancy, simpler package. But this is a fundamental issue. So the most latest models, they're a lot better now at solving these Olympiad problems. But famously, a lot of them still can't count how many R's there are in the word strawberry correctly. Very basic things. The way these models are constructed are not suitable for very low-level calculations. But for very high-level conceptual things, where humans can struggle, they can do very well. So people are finding ways to boost the power of these models. So one way is to force the model to not give the answer directly, but to think about it, pass it through maybe Wolfram Alpha, or maybe run some code in Python. Or if you want to prove something, there's some experiments where you ask the large language model to give you a proof, but give it the proof in the language Lean, or some other proof-assistant language, and then run it through a Lean compiler. If the compiler returns an error message, you bring the error message back to the language model, and the language model will try again and iterate until it either gives up or it actually gives you a proof. And in fact, that's beginning to work. For short problems, like problems on the level of our undergraduate homework exercise, they can begin to solve it by this way. There's some other strategies. Okay, so famously, a few months ago, AlphaProof DeepMind has a model which can actually was able to solve 3 out of 6 problems in the most recent Olympiad, not as fast as the human students. It took 3 days to solve one of the problems, for instance. And what they did was that, they treated, again, they had a human convert the problem from a natural language problem into a problem in Lean. Here's a statement in Lean, prove it. And they treated it like a massive tree search game. They treated, you can think of the act of finding a proof as just finding a path in a certain very large tree that would lead to a win at the end of your path. And they modified a previous piece of reinforcement algorithm called Alpha Zero, which is what was used to solve Go, to this problem. And after 3 days of access, using Google's supercomputer clusters, they were able to solve these problems. So that is a really impressive achievement. Training on a lot of data. So actually, one thing they did was that there isn't that much formalized proof data sets out there. There's maybe 100,000 proofs of formalized previous, which is not a very large set. They create like 1 million new proofs of various problems to solve. Okay, the tool that I use the most actually is, and I really like, it's called GitHub Copilot. So this is a fancy autocomplete that it's useful, like if you want to write LaTeX or Lean or Python or pretty much any standard language, you write your code. So here I'm trying to formalize proof in Lean, and if you pause, if you don't type anything for a while, then Copilot will suggest, it will just try to autocomplete for you what the next line of the code would be based on the previous lines. In this particular case, it suggested 2 lines of code, one of which was actually not correct, but the second one was correct. So you have to know, you can't just autocomplete, it will normally not work, but it can often give you a useful answer. Actually, it's particularly useful that if you want to do a repetitive task, like you want to write down 10 proofs of 10 similar different things. If you prove the first 1 or 2 of these by hand, this Copilot is extremely good at auto-completing the rest. It's uncanny, actually. These are quite useful tools. And so hopefully they're getting more and more integrated into these editors. You can use these hopefully we can use these formal proof assistants to filter out all the hallucinations and errors that these AIs make, and make them much more useful for mathematics. So I still think we are quite far from, there's this dream or nightmare, according to who you ask, of, one day you can just, type in, to GPT, solve the Riemann hypothesis or something, and it will just do it. It really doesn't seem to the current models, because one thing is that they rely very much on having a lot of data of similar problems in the data set. And the further you go out into research mathematics, the less data there is to train on. And so like rapidly you, basically, if you ask it for even just for ideas to solve a difficult math problem, it will basically suggest ideas that have appeared in hundreds of math papers already. It is very hard. It does very poorly in data poor environments. But they're very useful in other ways. I think they will speed up the way we write proofs. You can make conjectures. You can discover new connections between mathematical theorems. You can literature search. It's a semantic search. It's already very, very good at. And also it's a very good interface. If you want to like I use it all the time to run code. If I want to simulate to compute a function in Python or something, I'm not so good at Python, but I can just ask ChatGPT to give me the code. It almost always works actually. I think it will change the way we do mathematics. I can see in the future, right now we prove one theorem at a time pretty much. We prove a theorem, we write a paper, then there's another theorem that we prove, or we give a graduate student a proof or whatever. But you can imagine that if you have one theorem and you prove it, you give the proof and the theorem to an AI, and you say, okay, here are 1,000 other similar problems. Can you apply this technique to solve these other problems? And it will say, it will run it and say, oh, I can solve 265 of these problems by this technique, and so forth. I think we'll be able to sort of do mathematics on a much larger scale than we can do currently. Like the way that it's done in almost any other discipline, actually. Other disciplines have also sort of ways to do mass production, and now we're able to do so as well. Currently, I think the benefits are mostly at the fringes. It's really good at summarizing literature, doing lots of cleaning up data, writing code. I do hope that it will make proof formalization much easier and more and painless. Ideally, you should just explain your proof to a large language model, and the large language model will do the formalization for you, or at least break up your proof into lots of little pieces, and then maybe a separate AI will try to formalize each piece, and then there'll be just a few things left over that the human has to do. Yeah, in particular, I think one day the time taken to formalize a proof will be less than the time taken to write a proof directly, and then we will all switch over, or many of us will switch over. Okay, thank you very much.